All right, good morning. It's 11:20, which I think is actual starting time. Welcome to the first actual face-to-face meeting of the Quantum Internet Research Group. And I am Rod Van Meter. I am one of the co-chairs of the group. I know many of you in the room, but many of you I don't. So please introduce yourselves when you get a chance. The blue sheets are making their way around the room. And we have both a jabber scribe and a note taker, I believe. So I think we're in good shape there. Okay. Just quickly, some administrivia. You know when and where you are. The working group is up in Data Tracker, and there is also a mailman mailing list that is up that has been up and running for a while now. And this morning, as I was preparing, the version of the slides that I had still had us marked as a proposed working group, but I noticed in Data Tracker this morning that apparently while I was on a plane on my way here yesterday, Allison moved us from proposed to active. So we're now, I guess, an officially active RG of IRTF. Without yet having strong consensus on the charter for the group. And so I think that's actually one of the number one things we'll need to be working on very actively here is how to improve the charter and get it to what we want. So I am one of the co-chairs. The other co-chair is Stephanie Vayner, who is not with us here today, but we'll be working with her, and we have in her stead some of the people from her group are with us here. So the idea for this group, actually Stephanie was the one who originated it. She sent me mail in, I believe at the end of January this year and said, we should consider having a quantum internet research group inside of our IRTF. And I contacted Allison and she said, yeah, that sounds like a great idea. So I presented remotely at the IRTF open session in March of this year. The timeline was a little too short for me to get there in person. The mailing list was also opened in March. It's active and running. The volume of traffic on it I would characterize as low to moderate, so it will not overload you. And as I said, we were apparently approved as an RG on the 6th. Our tentative plan, which Stephanie and Allison and I have discussed, and which we discussed online as well, is for QIRG to meet 3 times a year, once at IRTF. I'm proposing that we should plan to meet for a longer, more extended session at Prague in March, and once a year at some sort of a quantum conference, and once a year virtually or online as a sort of meeting. So that's tentatively what the level of operations is this planned. The quantum meeting, I will be the general chair of the next workshop for quantum repeaters and networks, which will be in fall of 2019, probably early September, and probably in the town of Takamatsu. We're working with the hotels to nail down dates at the moment. So today's agenda, this sort of administrivia stuff just up for the first 5 minutes. Then we're going to have an introductory talk on the quantum internet by Axel Dahlberg, who comes from TU Delft. And then Axel will also have the responsibility of presenting the very first internet draft for the QIRG work, which is actually on advertising entanglement capabilities. Then I've set aside 15 minutes for actually talking about the draft charter, and finally any other business and open mic for 10 minutes or so. So any other comments or additions to this agenda? Any bashing that needs to be done of the agenda? If not, then I think we're good. All right, Axel, I think that's going to put you up for the first presentation here.
Okay, great. Can everybody hear me? Is this on?
Yeah.
Okay, cool. Yeah, so I'm Axel Dahlberg, and I'm doing my PhD with Stephanie Wehner at QTech in the Netherlands. And I should maybe say as a disclaimer, so my background is physics. And during the last year or so, I've learned more and more about networking and routing. But I'm pretty new in this field, and this is my first IETF meeting, which I found very exciting, and I'm learning a lot. And I will talk about the quantum internet today, and essentially a way to define certain stages of the quantum internet and what each stage allows for us to do, what applications we can perform in each stage. But before I do this, I want to give a brief overview of what is the quantum internet and what can we do with it. And just to get a feeling for who's in the room, I wanted to see maybe a raise of hands. For example, who knows what entanglement is?
Wow, that's excellent.
Okay, like half.
I think we know.
Yeah. Okay, that's great. So our goal at QTech is quite ambitious. We would like to enable quantum communication between any points on Earth. And that sounds very cool from a technological perspective. But why do we want to do this? Why do we want to build a quantum internet? The reason for this is that a quantum internet allows to do many cool applications, which are not possible in what we call the classical internet or the normal internet. And these things are, for example, the most famous one is quantum key distribution, where you can distribute keys using quantum mechanics, and then use these to do secure communication over the standard internet. There are also many other things, like you can do secure identification, you can synchronize clocks better, you can extend the baseline of telescopes, or you can even connect small quantum computers through the network and therefore have distributed quantum computation or even blind quantum computation. So this sounds great, very cool. So why don't we have a quantum internet already if we can do all these things? It turns out that building such a network is very hard, both from the point of view of developing the actual hardware to be able to do all these things, but also from a software perspective to develop all the infrastructure we need to run protocols and to control this network. And in QTech, we have a lot of people working on all these different levels, both in the experimental side and both from the software side. And we're currently now also part of the Quantum Internet Alliance in Europe, which is a collaboration between many companies and institutes to actually achieve this. And you might think that why are we already talking about the quantum internet? We don't even have quantum computers yet. But counterintuitive as it might seem, a quantum internet might be easier than building a quantum computer. The reason for this is that, of course, a quantum computer to be useful, it needs to have more qubits than you can simulate classically on a normal computer. And this is very challenging task. But for many of the applications you can do on a quantum network, you don't require so many qubits per node, as for example for quantum key distribution. And this is because these applications, the security are guaranteed by a property in quantum mechanics, which is called entanglement. So entanglement is a concept that have confused many people. For example, Einstein called it spooky at the time. However, since then we've gone quite far in understanding entanglement. And there are in fact two key properties of entanglement, which if you understand these, gets you quite far in understanding why entanglement is useful for applications in a network. The first one is it allows you to have complete coordination, which means that if you perform measurements on two qubits that are entangled, the measurement outcomes will be perfectly correlated, even though individually they're actually random. This is very useful for doing tasks which requires coordination between parties in a network. Furthermore, one can prove formally, due to quantum mechanics, that entanglement is inherently private, which means that no one else can have a share in maximal entanglement between parties. Or in other words, no one can essentially eavesdrop on these correlations that are being produced, which is perfectly suitable for example, key distribution. So entanglement can be produced in a network in different ways, but usually this concerns sending photons, for example, through a fiber, either to a midpoint or between parties. And of course, to have an interesting network, we don't want to put fibers between any two pairs of nodes in the network. And you might then wonder, how do we produce entanglement between parties that are not directly connected? And there is, in fact, a way to do this. So one can produce entanglement between two directly connected nodes, and also between two other directly connected nodes. And this midpoint can essentially do an operation and a measurement and send classical messages to the endpoints, which effectively produces entanglement between the end nodes. This is either called sometimes teleportation or entanglement swap. And a node or a device that does this in a network, we usually call a quantum repeater. And a network might look something like this. There are end nodes that are running the application. There are repeaters that extends the entanglement in the network between the end nodes. And at QTech, we're actually building this type of network right now. And in 2015, we made the first, what's called a loophole-free bell test, which is essentially a test that, without any doubt, guarantees that you actually had entanglement. And our next step in this endeavor is to build the first quantum link between the two cities of Delft and The Hague at about 25 kilometers. And this is our first step towards building our demo network in the Netherlands between 4 cities, which our aim is that this network will be universally programmable. This is not only a challenge in terms of developing the hardware that is needed, but it's also a challenge in developing the software. For example, to achieve this, one thing that we need to develop is a network stack for a quantum network, which, as many of you probably know, that this is a highly non-trivial task. And we have some proposal of what the quantum network stack might look like in a quantum network. But I don't have time to go into this in detail right now, but maybe this is something that is interesting to discuss, for example, in the next QIRG meeting. But what I want to talk about now is we have recently proposed essentially 6 stages of a quantum network with requirements on what type of operations you can do in the network, and then what each stage allows you to do in terms of applications. I would like to just point out that the network we're trying to build in essentially 2 or 3 years will be on this 4th stage here. So my plan is to essentially go through each of these stages and what requirements they have, and then what applications they allow you to perform. Maybe are there any questions at this point? Or any inputs? Okay, cool. So the first stage in a quantum network is actually the current status of this field, what's been implemented in reality. And we call this the trusted repeaters. And in a trusted repeater network, one can essentially, through the physical links between the nodes, produce key using quantum key distribution. However, why this is called trusted repeater is because if 2 nodes that are not physically connected want to communicate using this key, they of course need to trust the middle node through using both of these pairs of keys. This is why it's called trusted repeater. And this stage is slightly different from the other stages because it doesn't actually effectively allow for any quantum communication between the nodes. The next step is called a prepare and measure network. where essentially a node can prepare a qubit state and send it to another node, which can perform a measurement. This then actually allows to do quantum key distribution between any pair of nodes in the network, even if they are not directly connected. And it also allows for other applications, such as secure identification. The next step in these stages is when you also can actually produce entanglement. So in this stage, one can generate entanglement between nodes, and both nodes can then measure the qubits that are in this entanglement. This allows to do essentially the same protocols, but in a device-independent setting, where device independence means that you don't really need to trust that your devices do what they're supposed to do. Even the adversary could have produced the devices you use to generate, for example, key. In the next step, one can, additionally to producing entanglement, also store the entanglement in memory and do operations to this entanglement. And in this stage, which we're actually trying to build in 2 or 3 years, then opens up a lot of new exciting applications. For example, simple leader election protocols or blind quantum computation. And then going up further, I guess also further in the future, one can envision that each node can have a few fault-tolerant qubits, which means that you can essentially, by adding more qubits or making them a logical qubit by encoding them using error correction, you can reduce the noise you apply when you do gates indefinitely. However, the number of logical qubits you have at this stage is still possible to simulate classically. That's what differentiates this stage from the last stage, which is maybe the ultimate stage of a quantum network, where we actually essentially have connected quantum computers in a network. So these are the stages we have proposed, and are there any questions or discussions?
So I have an ignorant person's question.
Yeah.
Is it possible to describe the information?
Introduce yourself.
Sorry, I always do that. Aaron Falk, Akamai Technologies. Is it possible? Is there a zeroth order network where you are using binary information to communicate between quantum computers, and is that a useful thing? I mean, so you said you started out by saying you want a quantum network, but it seems to me that if you network quantum computers and using conventional technologies, is there any value to that? That might be something that is rapidly achievable and will have some.
Yeah. So possibly, I don't know if that would allow you to do anything more than, probably not, than doing whatever a quantum computer can do. But
I guess I'm trying to make the distinction between using quantum technology in the endpoints and carrying it over the network. And it looks like you're focusing really on carrying it on the network. And I'm trying to understand if there's any value in looking at sort of other points in that space. So like I said, it's an ignorant question.
Yeah. No, it's a good question. So I don't know anything that would allow you to do, which you cannot do essentially with just having a quantum computer. And as my guess is that a quantum computer will not be built before any of these things happen.
All right, I'll take chair's prerogative there and stick in one comment. Actually, there is a proof that if you just take two classical computers of a certain size and connect them together with only a classical channel, you get no net improvement in the computational capability over just having the two individual quantum computers. So it doesn't get you the big gain you might hope for. So ultimately, we do need this quantum-to-quantum communication to scale quantum computation. Right, one more question here, and then we'll go on to the next one. And if there are any other questions, we can save those for the open mic at the end here.
Igor Briskin, Huawei. Naive question. So you're talking about entanglement, but you haven't mentioned once decoherence. So the question is, can you do that? And is it an important topic to say, if you create entanglement, how do you maintain it?
Definitely, that's a good question. So I can say that I will talk briefly about this in the next presentation, actually. And there are things that you can do if your links, if you can only produce entanglement with a certain fidelity or with some amount of noise. You can also distill entanglement. And distill here means that if you produce sort of two bad entangled links, you can effectively combine them to a better entangled links. Something like close to how you distill, let's say, whiskey. So you can improve the entanglement even though you start off with a noisy entanglement. But then there's of course the question of decoherence. So if you want to store the entanglement, quantum memories are inherently noisy. So this you of course need to overcome. And this is also part of this fifth stage, where you can do gates in a fault-tolerant manner. So it's a very important question, but I don't have time to fully talk about this now.
All right, with that, let's go on to the next actual presentation. This is the first internet draft out of QIRG, and the first author of this, Kiriti, actually was here earlier this week but couldn't stay for Thursday, and I couldn't get here any earlier, so he asked Axel to take on the process of explaining this one.
Yeah, so this draft concerns advertising entanglement capabilities. For example, as you mentioned, how much decoherence you have when you try to generate entanglement. And this idea came up in a hackathon we organized 3 or 4 weeks ago on the quantum internet. And this the core idea was originated from Kiriti Melchior from Juniper and Stephanie Weiner at that time. And later, Christian also joined from Reddit. And so, as mentioned, we cannot produce entanglement perfectly. They will necessarily be, it will be noisy. And the question is, how do we communicate this in the network to make good decisions of how to produce the entanglement in the network? So I've already mentioned some brief things about entanglement, so I don't need to say this again. But I should maybe say that one might ask, what does good entanglement mean, or what does bad entanglement mean? And one can quantify how noisy entanglement is in what's called the fidelity. It essentially means how close am I to having essentially perfect entanglement. And of course, the fidelity will then decrease when you have decoherence in quantum memories. But this we need to then communicate.
Define perfect entanglement.
Yeah, right.
Making references to other subjective adjectives don't help.
Yeah, so there's a notion of maximal entanglement in quantum mechanics, where essentially means that you're, so I don't know how much I can explain for this in a way that doesn't require any quantum mechanics. I don't know, can you? So essentially this means that if you have maximal entanglement, what I said earlier, that if you measure your qubits, you will always receive perfect correlation between your measurement outcomes. But then if your state is not maximally entangled, you don't always get the same measurement outcome, that is perfect correlations. So you can quantify how noisy your state is by checking on how many times do I don't get the expected measurement outcome.
Sure, why not? Let's make this interactive. Go ahead.
No, it's a clarification question.
Yeah.
Can you just say if you change the state of a qubit in one spot, and if it's tangled with a qubit somewhere else, with no physical medium between it other than space, the state will change. So if I set a 1 bit in the qubit here, it'll be 1 over there. Is that a true or false statement?
So it will change the state, but it will not change the statistics of measuring the other qubits. However, it will change the correlations between the measurement outcomes. This means that there's no information being sent because from the point of view of the other qubits, if you look at that locally, the probability of receiving certain measurement outcomes doesn't change, but it's the correlation between these measurement outcomes that change. I don't know if that satisfies your your question, but we can talk more about it afterwards. So a quantum network might look something like this, where we have quantum nodes which can store and manipulate qubits. They can also send quantum information between the nodes. But there's also on top of this, of course, classical control nodes that essentially tell us what the quantum nodes should do, and they can also communicate classically. There might also be, so in here we assume that essentially the classical network essentially parallels the quantum network. There might also be classical connections where there is no quantum connection, but for the sake of keeping it simple right now, we will ignore these. So as I mentioned earlier, if two nodes which are not directly connected wants to share entanglement to do some protocol, they would need to produce entanglement on these shorter links, and then essentially these midpoint nodes essentially does a measurement and sends classical measurement outcomes to the end nodes, and we will then have entanglements between these nodes. But the question is now, if let's say the network looks like this, how do we decide if we should take, for example, this path or this path? This is not a trivial question to answer, because, for example, we might be able to generate entanglement faster here, but we might be able to generate less noisy entanglement in this direction. And as I mentioned, one can also do distillation. So one can produce two entangled pairs here, distill them to make a better pair. So this complicates the question of, should we go up or should we go below? So in this proposal, we don't answer how to answer this question. We only want to answer how should we advertise the capabilities of the links such that a decision could be made with some algorithm. And the features that sort of are important to know to make such a decision is, for example, of course, what's the topology of the network itself? What are the possible paths? What are the capabilities of each node? Essentially, how many qubits does it have? For example, how many qubits can I have in memory? And of course, what's the capabilities of each link? How good, in some way, possibly in terms of fidelity, can I produce entanglement in this link, and how fast? And am I able to distill this entanglement? So the proposal of this draft is to use essentially run a link state protocol to advertise these capabilities of the links, and add each of these properties of the links as TLVs to the link state protocol. And then each control node learns all the capabilities of the links in the network and can then possibly make decisions of which path to take. So, and I mentioned essentially all of these properties before. One thing that we should maybe mention is that Rod has already had a proposal of this in 2013, I think.
It's probably,
Where they essentially define the capability or the cost of a link as the inverse of the throughput of this link. So this may be good to have a discussion of between these two suggestions. Because, for example, whether or not you can do distillation between nodes might be important to make such decisions. So through this draft, there's a lot of steps to still be taken. So from QTech, we're sort of biased towards a specific implementation of a quantum network using nitrogen vacancy centers in diamonds. But it's also good to know, does this proposal also make sense for people that use other implementations, such as trapped ions or neutral atoms or something else? And we also want to put a short document on archive to explain a bit more about the actual theory behind this, and about entanglement and fidelity and decoherence and so on, to hopefully answer many of these questions that already came up here. So maybe questions to the research group itself is: does this fit into the charter, and is the mailing list a good place to discuss this? And, yeah.
This being my first time actually chairing an RG or a WG. In fact, I'm a little fuzzy on details of the process itself. This draft showed up with the label QIRG on it directly, but the group itself has not yet taken on responsibility for it. Looks like Aaron has a comment on that.
Sure. Aaron Falk, as a former IRTF chair, since Allison's not here, I can advise you that as the chair of the research group, you can run it in any way you see fit. If you want people to show up and participate, I suggest that you try not to annoy too many people in the room, so you might want to consider that when you make your decisions. But this isn't an IETF working group. You don't need to run a consensus process, and so I suggest that you do choose a process that's going to work for keeping people engaged and making progress and trying to achieve the goals that you want. Otherwise, whatever you like.
Certainly, I'm perfectly happy to have it as the first item on our agenda, working agenda. So it's totally fine by me. And the other co-chair is one of the co-authors on the draft, so presumably she approves too. So, other questions? Let's see. Is that it for the presentation?
Yeah.
Other questions? And state your name, please.
This is Dino. So Aaron asked the question, is there any value to run 2 quantum computers through a classical network? And you said there was no value add. So to move these properties, we would need this classical network. So it sounds like this is too far ahead of the game. We need to understand more fundamentals before we say how to do things, right? That's my gut reaction to this proposal. So if there's no value to have a classical internet between quantum computers, then why are we designing and putting a solution in place to put properties of quantum properties in a routing protocol that runs on a classical network?
Yeah, but so to clarify, so this is here you have classical communication between the nodes together with quantum communication between the nodes. And I think the question was whether you only have classical communication but no quantum communication.
If we want maximum value, or maybe even a little bit of value, we should have quantum nodes talk on a quantum internet without a classical network. Shouldn't we shoot for that as a goal?
Sorry, Dino.
Why do we want to shoot?
So I think if I'm understanding your question right, that's what Axel or Kiriti is actually proposing here. This is classical routing to control the quantum network, right? So
interject, maybe we could, Alistair Woodman here.
so your name, please.
Alistair Woodman, NetDev. I think we're trapped in a corner case of looking at quantum computing, quantum networking for quantum computing, which is, I think, a corner case question. The more interesting question, which I don't think anybody clearly articulated, is what are the practical uses of quantum networking for non-quantum computers? Is there any value to anybody to be able to, so you're talking about key distribution or faster throughput? There's a whole bunch of things out there that people are excited about, which may get people here in this room interested in what you're doing without the corner case thing of making both quantum computing and quantum networking work, which is probably 50 years away or wherever that is, right? But there may be shorter term practical interest here. And I think you're ducking what would I do with quantum networking with existing compute stuff?
Yeah.
Where's the value there?
So I should maybe say that, so this proposal of the different stages is also in an article on Science. So if you want to read more about what you can actually do in these different stages, you can also have a look there.
QKD is the obvious example, the quantum key distribution that already exists. It's an application for classical communications that uses sort of a minimal set of capabilities in the quantum world. And so part of the work item that's on the agenda is to figure out that full set of steps that go, the applications that go with the stages that Axel presented. So to go from there.
Igor Briskin, Huawei. I think the proposal is very similar to proposal of having, for example, a control plane that controls an optical network. Okay, so in this case, we have a control plane which have normal communication between the nodes, which basically auto-discover the property of the quantum links. For example, how many qubits you can have, what's the quality and stuff like that. And this knowledge will make it possible to create quantum links, right, between, say, node X and node Y, and provide the correlation to actually establish, say, end-to-end entanglement between two nodes. Does it sound like an accurate description?
Yes, I think so. If I understood you correctly, yes. I mean, we will definitely need classical communication between the nodes to build a quantum network. That's without a doubt. For example, only to, for example, synchronize the nodes. If you want to send out photons, you need the photons to arrive at the same time. And this you need to synchronize. However, this proposal is simply to also advertise the capabilities of each link to make better decisions.
So it's this is approximately the same way as we, for example, control optical trail, right? It's not really like a normal communication. It's just a data plane of in optics, but we do exchange information, like routing information about the capability of optical links. So we could produce, say, end-to-end optical trail with certain characteristics along the trail. So if I understood it correctly, and the goal is to create a entanglement between, say, two either directly or not directly connected nodes, then I would need to know the topology of my quantum links and intermediate points and set up this entanglement in such a way that it will work end to end, right?
Yeah.
Let's make this last question for now.
Okay, Dejan Bogdanovic. I'm a little bit, confused with this request and essentially, and this draft I'm trying to think about. But one thing which is much more interesting thing to me is how to carry more information in a single photon over the network, because this could vastly improve the capacity that we need, and probably, it sounds crazy, but it could end up being cheaper than how we are doing the optical networks today. So that's one area that I occasionally read upon and is quite interesting. So using classical networks to distribute information, whatever that information is, I mean, we've been doing that, and I fail to see here. I mean, there are some problems, but I don't understand them. But as I said, that's one of the areas that will be very interesting to me.
Robert Groberg here. One suggestion, right, just to get everybody up, right, you might want to use QKD as an example with trusted nodes, the way things are done today, and untrusted nodes, and that might educate people in a fairly simple way, how, the simplest thing that you could do with a quantum network, right?
As a comparison, you mean?
Yeah, exactly, right? Because it's just, the issue of using, ISIS or TLVs to explain fidelities and things like that, we already have that concept, right, for best path and things like that, right? So using this in the quantum space is pretty simple, but I think people are having a hard time understanding why.
So you mean as an example for quantum internet?
QKD is a really simple example, right?
Yeah.
That people understand, I think, at some level, QKD, right?
So Axel had the slide in the previous presentation talking about the trusted repeaters. Did that not come through?
No, I don't think so. People think of, Beijing to Shanghai, right, as, QKD across all these multiple hops, where it really isn't, right?
So I think we have one question from online. Said, I pushed the red button. All right. Do I have to hold it? They may have. I think it was Melchior, but he may have stepped out of the queue. I no longer see him listed up here. Melchior, question online? Okay, now I think we got you.
Hey guys, Melchior Ammons, I'm one of the co-authors of the draft. So I think we might need to be more clear on what the objective is we want to get to. So our intention is to distribute data and information we need in order to form the entanglements, right? So the endpoints need a way to communicate with each other and to distribute the information they would need to build that entanglement. So yes, agreed with the previous speakers that ideally you would not need extra links or a classical network. The fact is now that we do need that at this point. So I just wanted to state that. Thanks.
Okay, thanks. I'd like to cut this off here so that we can go on to the last couple of things on the agenda because we only have about 19 minutes left. Axel, thanks. Let's see. The other item, I may have lost a link to this. Hang on. I do not have separate slides for the draft charter. So let me pull that up here. Hang on. All right. Tell you what, let's do it this way. I thought I had this up in a tab, and I realized I don't. Sorry about that. Mailing list. Yeah, archives. Yeah, the one that's actually in Data Tracker was just a placeholder, and I thought it was the whole thing. All right, let me see if I can pull this up in a way that's reasonable. Make this bigger. Not having the ability to pull this up larger. All right, so the charter, this I sent out to the mailing list just on Tuesday. If you want to look at it, you can pull it up online through the mailing list archives. The set of kinds of problems, there's a sort of a prologue with this set of kinds of problems include routing and resource allocation and connection establishment, which is one of the things we've been working on lately, interoperability between different kinds of networks, security of the system of quantum internet operations, as well as the end-to-end applications, and design of an API that will serve the same role that sockets performs in the classical internet, which I think is actually related to some of Axel's own current work, although he didn't talk about it today. But there are also a set of other problems, including the applications for a quantum internet, which has already been brought up here a couple of times, figuring out how to take that set of 6 stages that Vayner and company have proposed and figure out what applications each of those will do with relatively concrete use cases for each one, I think is one of the big items for the entire community, not just for a handful of people here and there. And then a little farther away, there have already been people who've been working on how to build not just entanglement between two nodes, but how to make use of larger entangled states that cover multiple systems. And so that can be something that's farther on down the line. For outputs and milestones, two concrete suggestions that I had are, first, an architectural framework that delineates the types of nodes. One of the figures that Axel put up there, he mentioned repeater, and I think there was switch and there was end node on the list. Is that a complete taxonomy of the types of nodes that we have? This, I think, has been brought up before, that we need some sort of shared common vocabulary in order to move forward, in order to actually take steps toward a complete network architecture. So I think that, plus working on these this set of concrete use cases, plus now the third item also of this draft for routing that Kiriti actually wrote, I think that gives us a solid first three items on our work agenda here. And as I said in the introductory comments, I think the plan is to meet once a year here at IETF, IRTF, once a year at a quantum conference, and once a year online. So I want to open the floor up to comments on this draft charter. So far, this is essentially first light for this charter. No one but me has seen this and looked at it, so I would like to have your all's feedback on this.
Hi, Aaron Falk. So one of the questions I think that you have to ask when you're creating a new research group is, does the existence of the research group, is it going to bring in the right communities that you want to collaborate? Just judging by the number of people in the room, you've gotten the attention inside the IETF.
I'm thrilled. So for those of you who are online and can't see the room, I haven't seen the blue sheets yet, but we've had 80 or 90 people at least in the room here.
Yeah, I'd say about 100.
Yeah, I think it's probably close to 100.
And but I guess the question that I have is like this: there's a lot. The topics that you've got here rely on domain expertise that is not sort of the core IETF expertise. And so, are you going to be able to get those people into the room? Have they already shown interest? I don't know enough to recognize the individual names, so I'm just sort of asking this of you.
Yeah, the physicists, certainly the people who are the experimentalists who are building these systems, certainly have none of the knowledge that's in this room. And the question is, do they recognize it? Do they think that that's important? And are they willing to come and participate in it? That's the open question right now. The EU Quantum Internet Alliance that Axel presented is probably the largest coordinated effort on the planet at the moment. So clearly we need the involvement of some of those people. If we don't, if this forks off from what those folks are doing, then this RG will have no impact on what they actually build, right? So it's absolutely critical that we have some involvement with them. Axel's a theorist and a software guy. Stephanie herself used to work for some ISP in Europe before moving into quantum. But the other key part of the Delft group over there is actually a guy named Ronald Hansen, who's the leading experimentalist and building these systems that he's talking about. So they sit in the same building. So at least on one key hardware project, there is direct collaboration going on, and a path for people in this room to influence what that group does is through Axel and Stephanie. That's sort of what you might call a second-class route to getting things done. We would be much better off if we can get some of them to actually show up in person and actually contribute on the mailing list. And so I think a key goal actually is, if we're going to meet face-to-face in Prague, is that we need to say, if QIRG is going to be viable, we must have at least one experimentalist in the room in Prague.
Hi, this is Dino. I think that group of researchers or the physicists have to actually teach us, because if we don't understand the underlying properties, then we don't know what the value is. We can't make good trade-offs, that sort of thing. So yes, we have to influence each other, but I think more to the point is we have to be taught by the physicists, and we have to teach you guys about networking, right? The same sort of thing.
Yeah, I mentioned in my opening remarks that the third workshop for quantum repeaters and networks, The first one was, let's see, so 2019, 2015. And in that one, we actually started with a half-day tutorial, and we had people like Paul Makapetris and Bill Manning and Kaveh Salamatian show up for that. We would be totally on board with doing that again anytime, any place that makes sense. So if we want to do a half-day tutorial on what quantum networking is in Prague, if people would be up for that, I will totally put it together. We'll put together multiple speakers and we'll bring people and do it. If people are willing to commit, to spending, several hours sitting in the room learning about it. Okay, how about show of hands for people who would sit in a room for a half a day to learn about quantum networking in Prague? All right, that's 80% of the room. So I think that's a yes. All right, that's on the agenda for Prague. I'll make it happen.
Yeah, Michael Arbenz, I agree about the educating us about it and educating the people there about routing. And I think from my limited understanding, the analogy about controlling an optical network is, I think, seemed to be the closest we have so far of what this is. I mean, we don't really need to know the details of what the photons that are going on, as long as we understand the properties and the optimizations that should be done. And it could also be that what you need is not what we have done here previously when it comes to like optimizing the path, or I mean, people know a lot about those kind of optimizations here. So if there is anything, I mean, if you don't want us to know and we just want a routing protocol, and you put in, if you can elaborate on exactly what you need and the optimizations you want the routing protocol to do, we can probably do it. But if we understand it better, we can probably do a better job. But I think it's all about perhaps we don't need to understand the physics, but we need to understand enough about the properties and the requirements that need to be done. So and finding analogies, I think, also for people who are not heavy in physics background.
Eric Nordmark, this might be a bit of a nit, but if you scroll down to the end, there was something about working with other STOs, which sort of stood as like coordination point with other standards organizations. I mean, inviting people to participate from a research perspective is fine. You don't want to put yourself in a space where they will send you liaisons and expect you to respond, because that's not something that research groups typically do. And
Good point.
The IETF can do that because it's an STO, right? But yeah, invite people that are doing research. So.
Yeah, I want the weakest possible word that would include this. Maybe the weakest possible thing is to actually delete it. I'm not sure, for those of you who don't know, there is work going on. Both ITU and IEEE have started some efforts around standardization of quantum networks. Nothing that's looking quite as far forward as the total set of things that Axel talked about so far today. It's much more short term. For example, the IEEE group is working on essentially open flow control of QKD flows on trusted repeater networks. There's an IEEE project that has been stood up that's been doing that, and they've been working for, I think, about 2 years on it. Yes.
I don't know what to do with that information. Alistair Woodman, NetDev. So again, I'm speaking just for myself, but there's, and I'm a physicist, so I might be at a slight disadvantage here, but you're not doing a good job of sort of articulating. We saw the roadmap thing. What we didn't see, I'm sure there's a bunch of people in here, and we heard from one speaker already that want to know when we're going to get more bandwidth than we had before. There are some people here in the room who want things to happen instantaneously across the planet, right? And there's no clear statement about when you think those things may happen from a temporal standpoint in our world, right? At the moment, I'm guessing you're going to be talking about 9,600 baud communications for the next 5 years. Maybe it would be a good idea to tell everybody that, because maybe a lot of people would just go, "Oh, thank you, I can move on," right? So there's a specific set of things you're looking to get skill sets in, right? And maybe the socket stuff is a good area, and all those other. There's a whole bunch of people here turned up to understand what's going on, and maybe we do need a full half day to talk about that. But I think there's a very highest level. There's no clear understanding about when's this going to inflect, and in what particular applications does anybody expect this to inflect.
All right,
become mass interestedly useful for people, or do you need people to build boxes, or what do you need, right? Because I think we've got very disparate skill sets here, and I'm guessing you can use 10 to 20% of the people here, and the other 80% of the people are just trying to figure out, and they will figure out at some point that this is not their space for the next 10 years. And sorting that thing out earlier would help.
Thanks for bringing that up. Actually, when that question was when that point sort of went by during the Q&A about Axel's first presentation, I sort of deliberately didn't interrupt and say that because I didn't want to derail the presentation. But if you are thinking that quantum is a possible way to get higher bandwidth out of your networks, you're thinking wrong, right? That's not on the agenda, right? So the data rates that people are talking about so far, the quantum key distribution, the point-to-point boxes, some of those go as high as what, maybe a megabit per second or something. Although that's sort of, they're possible big leaps that could be had on top of that. But for these entangled networks, the people who are doing this, the group in Delft that's doing this over 2 kilometers of fiber on the Delft campus, their data rates for doing this are creating 6 entangled states per second. Is that right? Oh, they're up to 30 now. Sorry, that's right. In fact, Ronald told me that when I saw them recently. They're up to 30 entangled states per second on this. So the point in doing this is not bandwidth, right? Any sort of thought of that needs to just walk right out the room right now. The point in doing this is with those entangled states, you can do certain things in new ways that circumvent that need for more bandwidth or fewer rounds of communication in particular is one common one. So I divide the applications up into essentially 3 areas. They're sort of similar to what Axel talked about. One's distributed computing, which is relatively straightforward, and we talked about that. The second one is cryptographic protocols, which includes QKD. And the point of QKD is not to generate keys faster than you can do them with Diffie-Hellman. It's to get new security capabilities that you don't have in existing software systems. And similarly with quantum Byzantine agreement, which would also be in the same area, in theory, it's going to give us better security properties than existing cryptographic-based Byzantine agreement protocols. Whether or not that's really true in practice, I think is very much an open question and needs further discussion. And then the third area, which Axel also mentioned, is that these can actually be used to enhance the precision of sensor networks, including things like interferometry between large radio telescopes or large optical telescopes, for example. So in those 3 areas, but none of this is about bandwidth. We're not going to be talking about, quantum networks lets you go from 40 gigabits per second to a terabit per second on a fiber. That's not the point. Yes, question.
My name is Igor Briskin, and I'm a specialist in the optical control plane. I have very limited understanding of optical data plane, but still, if we managed to describe the optical networks and the optical links and also optical nodes and what constitutes a good optical path, and based on this knowledge, we could run various optimization algorithms and can make it happen, make optical OSNR like reasonable and the signal readable and so forth, without actually full understanding what's happening in the optical data plane. So what I'm saying is that we can have a very similar paradigm in cooperation between, say, IETF specialists and quantum physics. Okay, we do need some limited knowledge. We do need to understand what the underlying processes happening, but we can also basically take advantage of all the knowledge we had so far.
Thank you. That was just a comment, right? I don't need to respond to that. Thanks. Let's make this the last question because it's now 12:20.
So, Stuart Bryant, I've been very much a novice on this, but two observations. First off, the time transfer solution is one that is taxing the network industry. Some of the new radios, particularly 5G and presumably what goes on afterwards, have critical requirements on exact time transfer that stress GPS to its limit. So there's a major win to be had in that. And time is not a high bandwidth thing because once you know the time, then you know it, right? So that's a really important area, I think, to think about. The other thing is that I observed a paradox in what was being described. If one of the functions of quantum networking is to improve the security of a network, how do you use a classical network to connect nodes together, which is presumably vulnerable to classical security errors? I don't see how you get the bootstrap to work that way around.
You've asked the $1 million question there. Part of the answer to that is that, in fact, some of these security protocols that depend on end-to-end entanglement allow the two end nodes to confirm with each other that they actually believe that there is no one in the communication channel. But if their classical communication can be disrupted in real time, including the breaking of whatever encryption they're using for that classical entanglement, yeah, you've got a chicken and egg problem there. It's an open question. Let's see. It is now 12:21. People are probably interested in lunch. I hope this has intrigued all of you, and we will work to have a half-day session available in Prague, a tutorial session. Please join the mailing list. There are reference materials, including for beginners, available in the mailing list archives. And if anybody's actually interested, Shota Nagayama, who's sitting right up here in the front, is putting a group of people together to go to dinner and talk about this tonight. So find Shota if you're interested. Thank you all for coming.
And if you haven't signed the blue sheets, please do so. And where are they?
Hi. Nice to meet you. I have a couple of document numbers, but there's a proposal from SK Telecom, and they are working with IETF103, which is one of the QKD box providers from Geneva. I don't know the answer to that because I don't do any IT stuff at all. But one of the guy that I'm on an organizational board with is one of the Japanese government's advisors on security issues. So he asked me about. We don't like He sent me a couple of draft documents and asked my opinion on them, and I sent him my opinion. So.
And what does it mean to have like two qubits on the other side of an IGP? Yeah. Why to put it in
I would like to do it early in the week because I need to be back in Japan. If that's your question.
Yeah.